So should be recording now. Hi everyone, and we're very excited to have Faidra Monachou today as our speaker for the Theory of Computing for Fairness seminar series. So Faidra is a PhD candidate in MSNE right now at Stanford University, and she's advised by Professor Itai Ashlagi. So she's interested in market design, and her work has been focusing on the role of discrimination, diversity, and information design in education, sharing economy, and on matching markets. And so she also co-chaired the workshop on mechanism design for social good last year, and she's currently a co-organizer for the Stanford Data Science for Social Good program. Take it away.
Yeah, thanks a lot for the introduction. So I'm very happy, and the invitation, and I'm very happy to present our paper on dropping standardized testing for admissions, differential variance and access, which is joint work with Nikhil Garg and Hannah Lee. I think they might be on the call right now. And a preliminary version of our paper appeared at FACT a few weeks ago. So in 2018, University of Chicago was the first top research university in the United States to drop the test score requirement for American applicants. And from 1957 to 2018, when Chicago took the decision, the university had required prospective freshmen to take some form of a national level test. And before that, it screened applicants with its own test. So the debate about standardized tests recently came again to the spotlight when, as you may have heard, University of California suspended the requirement that applicants from California this time submit the SAT scores and announced that it has plans to design its own test for its applicants. So independently of this decision, we also saw that the COVID-19 pandemic created another trend of waiving the test score requirement in admissions. And until today, we know that hundreds of colleges have stopped requiring the SAT or ACT, at least temporarily. The use of standardized tests in admissions is an open and difficult debate. A common question is whether dropping test scores will help expand access and equity, or instead lead to the admission of less prepared students. And so far, test scores have, of course, played an important role in admissions decisions. And in fact, their use started in the previous century with the goals of rewarding academic merit, breaking social class barriers, and giving all students equal opportunities. So proponents of test scores actually claim that standardized tests offer a systematic means of collecting information for applicants, and have concerns that the bias we see in other application features, for example, we know that recommendation letters have a lot of bias, might be greater than the bias we see in tests. And the most important concern that they have is that actually dropping test scores will lead to a ban-the-box or statistical discrimination type of effect. So this effect can potentially arise due to bias in terms of differences in the mean between groups, but it can also arise due to differences in feature precision, as we will see in this talk.
Just out of curiosity, what's ban-the-box?
Yeah, so it's a term that actually describes a campaign that started in Hawaii in the late 90s. So there was a movement asking employers to remove from application forms a checkbox that actually was asking the applicants to say whether they had a criminal record or not. And the reason for this movement was that it would help ex-offenders find job more easily. But what economists found later is that it actually created a statistical discrimination effect where employers would be hesitant to hire young, low-skilled Black men because of differences in the numbers of ex-offenders between different groups. Okay, so here in this slide, I have a sentence taken from a New York Times article, and I think it nicely summarizes this very intuitive concern. So to rephrase it, the concern is that in the absence of standardized testing, a capable student from a little known school may be more challenging to evaluate, and this will further benefit students from privileged and historically familiar backgrounds. So for example, this is of course a very hypothetical scenario. Suppose that until now, Stanford used to admit a lot of students from Palo Alto, but also some students with high test scores from other less known high schools. So dropping test scores might lead Stanford to the less, let's say, risky decision of admitting more students from Palo Alto and less students from the less familiar places. So this is what proponents of test scores say. And let's now see like the other side. So on the other hand, dropping test scores might help expand access and equity. And it is well known that test scores exhibit racial gaps and might also reinforce existing inequalities in higher education. And most importantly, there are several barriers to testing for certain groups of students, both in terms of test preparation, but also to the access itself. So I want really to emphasize like this disparate access to testing, and here's some statistic highlighting this disparity. So for example, 8% of lower income students compared to 78% of high income students use a test preparation service. And we also know that for every 10 poor students who score college ready on this test, there are 5 other poor students who would score college ready, but who just like take neither exam. And last, to connect our motivation inspired by Berkeley's decision I talked about, it was interesting to see that after dropping the GRE requirements, UC Berkeley saw a 82% increase in the number of underrepresented minority applicants to master's program this year. Although I want to say that it is important to acknowledge that this effect may be due to the pandemic and not the decision specifically. So it's hard to know yet. So motivated by these competing claims about the role of test scores, in this paper, we provide the theoretical framework to study the effect of testing requirement on academic merit and diversity in college admissions at the single Bayesian school. And really our goal in this paper is to shed light on this debate by highlighting the trade-off between 2 key factors when thinking about test score policies. So the first is the test scores and other application features informativeness in both groups. And the second is access barriers to testing. So today I will focus mostly on the role of informativeness, but later in this talk I will talk about how this trade-off between the 2 arises when we include barriers. And as we will see soon, sorry?
Yeah, sorry, another question.
Yeah.
So when you're talking about test scores policy, it's like it's binary. It's either keep it or drop it.
Yes, yes.
That's right. Right.
Yeah.
Is there something like, is there discussion of, I don't know, like improving the tests or somehow?
No, we don't look at this question, but I think like, yeah, we can talk about this later too, but I think that that's another aspect that we don't look at in this paper. And of course, I think like, for example, like Berkeley has this goal of improving the test. So maybe it's a solution that we could consider. So as we will see soon in the talk, informativeness in the sense of test scores and other application features variants really matters and has an ambiguous impact on disparities. So we characterize when dropping test scores can harm or benefit different groups of students. And specifically, we saw that due to information loss, dropping test scores may sometimes lead to a less diverse, less academically qualified class. But if we have substantial barriers to testing, then dropping test scores can improve both academic merit and diversity by increasing the applicant pool size. So in the paper, we have several results like theoretical results, simulations, and a data application from the Texas Higher Education Opportunity Project. And today I will talk about most of those results. Okay, so now I hope that the motivation was clear. So in the rest of the talk, I want to focus on the model and some simple intuition first, and then our theory results and a brief overview of a data application. So let's jump right into the model. We consider a single school here with a limited capacity C, which receives applications from a continuum of students of mass normalized to 1. And we consider that there are two social groups of students, A and B. And as we will see on the next slide, these two groups might differ in their characteristics. They might differ in their size, but we don't make any assumption on the size itself. So each student is characterized by a true skill level Q, which is drawn from some normal distribution with parameters mu and sigma. And this distribution is common for both groups A and B, meaning that the two groups of students are born equally skilled in terms of this Q. And then the school does not observe the true skill Q of an applicant, but instead observes some noisy features theta K, which are the sum of a student's true skill Q and some Gaussian noise, this epsilon here. And the parameters of the noise distribution can differ, first across different groups, but also across different features, both in terms of the mean and in terms of the variance. And this noise epsilon will be dependently drawn for each feature, but the features are otherwise correlated because of this dependence on Q for all of them. Okay, so now let's just use this simple model I just described for a simple exercise looking at how a Bayesian school would make decisions about students. And to start with some simple intuition, let's look more closely at the estimation process of the school. So for every applicant, the school will observe two things: their group, where they belong to. So there we say that they're group aware, and they will observe some subset of their features. So to simplify the math a bit, let's look at each step for a single feature, and everything will easily generalize to K features later. So if we take the two different candidates, one from group A and one from group B, their true skill level Q will be drawn from this distribution I told you, and mu and sigma will be known to the school. So the school will not observe Q, but will observe this theta, which is the feature, and it's a sum of Q and epsilon. We see that parameters, again, might be different for the groups. So since the school cannot know the true Q, but they observe both the value of theta and G, then it will naturally compute the expected value of Q conditional on all the information they have, so theta and G. And this is what I will call from now on like Q tilde or perceived skill estimate in this talk. And one quick and very simple observation is that statistical discrimination effect immediately arises. So if we take two students from different groups, one from the green group A and one from the pink group B, who are born with the same true skill level Q, and we assume that they happen to also have the same observed feature theta, then the school will very rationally have a different estimate for each person because like all these parameters are different. And eventually, the school will repeat this process for every student. So they will aggregate all these estimates per group and we'll get another normal distribution per group, like this distribution here. And this distribution of perceived skill levels show that the estimation process of the school has two properties. So we can see first that although we started from two noise distributions with different means, so mu A and mu B, the distributions of this Q tilde here have both the correct mean mu of the original true skill level distribution. So this is the correct mu. In other words, the school successfully eliminates the existing bias. On the other hand, we also see from the variances of those distributions that the school knows that the two groups have the same distribution of true skill, so they shouldn't differ, but the school fails to correct the variance. So here is a summary of what I just told you. And let me generalize exactly the same thing to K features. So the school is group aware, observe the group, as we said, and some feature subset set. Then they compute the perceived skill estimate for each individual. And then they just aggregate by repeating the same process for all applicants. So the school will get this distribution. And compared to the case with one feature that we saw before, the variance simply now depends on the sum of precisions of the features in the set S that the school takes into account. So this is the only difference with what I told you before. So what is missing here? So far, I haven't told you anything about the relationship of those variances. And most importantly, this talk is about like discrimination, but I haven't talked at all about disadvantage or fairness. So the convention we make in this paper is that group B students face what we call an informational disadvantage due to unequal precisions across the features. So what specifically this term here means is that the total precision for group A, it's or like privileged students, as we will call them. So group A is the privileged students, is higher than the total precision in the features of group B or disadvantaged students here. Questions? Okay. So given this theoretical framework, I want to use like these basic tools to describe some of our results and try to answer the question of dropping standardized test scores. So I will talk about these results looking at several policy schemes. So to compare the performance of these policies, we need some metrics, and we'll look at three different metrics. So we look at academic merit, which is the expected skill of admitted students. Second, diversity level, which is the fraction of group B or disadvantaged students in the admitted class. And finally, the individual fairness gap, which is the difference in admissions probability between two students of the same true skill queue, but different groups. And to be a bit more specific, it is basically the probability of admission of a student in group A minus the probability that the same skill student in B has. And as a result, when I say that this gap here is positive, it will mean that the disadvantaged students at the specific level Q are being discriminated. So the school's goal for now is to optimize academic merit. So this is what will play an important role in their decisions. And based on these metrics, we will evaluate three policies. So a policy with tests, which will be our baseline, then a policy without tests, and then finally policies with affirmative action. Okay, so let's start with our baseline policy, which I will call P full, and basically takes into account all K features included in the test. So like this is our first main result, which utilizes the intuition I have presented so far. So what are our findings? Under such a policy, we find that disadvantaged students are underrepresented. In terms of individual fairness, we find that very high skilled students in group B have lower admission probability than same skilled students in group A. And in terms of academic merit, what we see is that not only group B students are admitted at a lower rate than A students, but the targeting of high skilled students from group B is worse. So the academic merit, maybe in contrast to what we would expect, the academic merit of the few B students that are admitted is actually lower than the academic merit of A students that are admitted. So why do these things hold? Remember that earlier we derived the perceived skill level distribution. Here it is. So let's now see how admitting according to these estimates impacts diversity. we know that the school optimizes for the academic merit of the admitted class, right? So it naturally wants to look at this distribution and just admit the applicants with the highest perceived skill estimates from its group. And these are exactly the students that the schools perceive to be actually high skill. So like it's very not rational to do so. And even though we start from the identical true skill level distributions, so like both groups are equally skilled, and the school is Bayesian optimal, then our assumption, like this assumption that I told you about the precision difference between A and B, leads actually to lower variance in the aggregate perceived skill level distribution for group A. So in other words, the higher uncertainty in the features of disadvantaged students in group B leads to more conservative estimates for their skill at an aggregate level. And as a result, we see that this greater concentration around the mean compared to group A. And this can be easily concluded from the resulting variance in the perceived skill level distribution of group G. So since this condition holds here, the resulting variance in group A is higher than that of group B. So this in terms implies that the greater mass of group A students, so like if we look here, will be considered to be high skilled. So now when the school comes and wants to set an admission threshold in order to admit the students above this threshold, more students from this privileged group, the green distribution, will be perceived as high skilled and as a result will be admitted to the school. So this is a point where the assumption that I told you, like this selectivity assumption that the capacity is smaller than 1/2 is important because it implies that we are on the right tail of the distribution here. So in other words, as I think it's clear from the picture, privileged students are admitted at a greater rate than disadvantaged students, and this naturally leads to the underrepresentation of disadvantaged students at the school. And of course, like you may say, okay, how bad is like the diversity level? Then the exact level of diversity depends, of course, on the informativeness gap. So like how big the difference here is. And as we formalize in the paper better, a larger precision difference would lead to lower diversity. I think there is a question.
So I guess I wanted to understand the result a bit more. So so we are calling the group A as advantaged group here, is it?
Yeah, privilege, advantage, yeah.
And then do they have more informativeness that is less variant?
Yes, yes.
So this, I feel like this goes against my intuition that SAT scores would be more informative for actually disadvantaged groups, but because for rich people, stat scores are not informative about their.
Yeah, so an important assumption here is that we assume informativeness across the total feature. So we don't say that the test score is more informative for one group or another. So really the assumption here is about the sum, right? So like there are many features, like we take into account recommendation letters, we take into account like all these essays, like all these things. So I haven't assumed anything about the test scores, and I will not assume anything about the test scores. So like I will not assume that it's more informative or not, although we can later discuss like what I really think happens. Okay. Yeah, thank you. Okay, so this was about diversity. In terms of individual fairness, I remind you that the result was that very high skilled students in B have lower admission probability. And in fact, we characterize the full condition under which the individual fairness gap is positive. And before I give you that condition, here is an alternative plot that is based on our simulation results. And I want to use today to convince you about these statements. So on the vertical axis here, we have the true skill Q of a student. And here we have the perceived skill estimate Q tilde. And with the green color, again, you see the privileged group. And with the pink color, you see the disadvantaged group. And with the gray area here, we have the admitted class. So this was the admission threshold. Okay, so like this is the admission threshold, and what the statement says is that there exists some other threshold here, like this is the threshold we have in the characterization, such that if the true skill level Q of a student is above that value here, then the individual gap will be positive. So students like in the disadvantaged group will be discriminated. And if it's below that threshold, it will be negative. So graphically, like we can take this example here. So if we take all students with some high value of true skill Q, so this is a high value, in the plot, we see that the greater mass of the green group here, the privileged group, is admitted compared to the pink group and the mass here that my pointer shows. But if we go to a low skill Q here, we will see that those pink students, the disadvantaged students who are low skilled, have low, like it's very low, but still higher probability of admission compared to same skill students from the green group. And in terms of academic merit, I will use again the same picture. So to remind you, we find that disadvantaged students have lower academic merit than admitted privileged students. And the intuition again can be seen in the picture. So if we focus on this gray area of the admitted class and look along this vertical line of admission, then we will see that the pink students, the disadvantaged students here, are admitted relatively uniformly across the spectrum of different skill levels. But if we look at the green group, we see that the school manages to identify here the high skilled students much better, and as a result correctly admit those students at a much higher rate. Okay, questions?
Actually, I just want to clarify, like, what is the, can you just say again that what is the exact admission process you're considering? Is that the school first do an estimate based on the group information and the samples they get, and then based on those two estimates for different groups and the merit, sorry, they set a threshold.
Yeah, exactly.
So, like, why do we assume that the group would use the group information in order to set the threshold? Is that a reasonable model?
First, like we focus on this in the paper, although in the end, I can show you some results about when we don't assume this, or when we don't assume that we see the group. And there are many reasons why we make this assumption. So first, like based on the legal framework, we know that in admission, the school can use race, you know, like protected characteristics like these in the application. So they ask for this information and they can use it to adjust for different things, but they cannot use it to give preferential treatment to any group. So what we do here is exactly, you know, what the legal framework describes. We can use the protected group to actually estimate these different parameters, and it's optimal to do so, because if we don't take the group into account, then we actually will have a suboptimal outcome, and I can show you the plots in the end if you're interested. It's not only legal, but it's also natural to do so, like if the school wants to indeed admit the best.
I see. So you're saying that under the legal framework, it's actually illegal for individuals if I take into the information of the race. So one way to use the group information is to learn some sort of group statistics.
Yeah, so in admissions, you would say, and like based on my discussion like with different people, like you can say that we see that a student struggle, for example, like it's coming from a disadvantaged background, so we'll take this into account when we evaluate their application.
I see.
Okay,
I see.
so it's
Thank
a practical way. Yeah.
Thank you.
Yeah, thanks. So now that we have
another question.
Okay, sorry.
I'm wondering if there is like a formal relationship to the impossibility theorems in fairness?
Yeah, so there is. What we find in terms of this impossibility results is that group fairness cannot be satisfied unless we have equal precision. So unless like these two sums are exactly equal. And in terms of individual fairness, it's again the same result. So it will always fail unless we have equal precision.
Yeah, so basically it follows, I can like map the concepts that you talked about, like the academic merit kind of seems like a calibration requirement, type requirement, and the other one, the individual fairness, kind of looks like what they call balance for the positive.
Yeah, it's
graph.
definitely, it's individual. Yeah, it's definitely inspired by like the notions of fairness we see in the literature. Yeah, and it's a relaxed notion of all this. Yeah. Okay, so I think I'll continue here. So far we have developed some intuition from our baseline policy, and we are now ready to use these methods and tools to look at our main question that they promised. What happens when we drop test scores? So how does the new test-free policy compare to our test-based baseline? And for simplicity, we are going to assume that the feature K is a test score. It doesn't really matter. So the P not test policy is going to be our test-free policy. And we will compare it to the P full policy I was talking before, which was with tests. And what we now see is that the diversity level might decrease. The individual fairness gap might increase for high-skilled students. And the direction, as we will see, depends exactly on the informational environment that we are in. And what we know, and it's bad news, is that academic merit will decrease for both groups in any case. So let's first look at diversity after dropping test scores. I remind you that we have assumed this condition here. So the inequality is this way. Group A has higher precision. And we see that if we dropping test scores reverses this condition here. So if we exclude this K feature, then group B has higher precision. Then diversity increases after dropping the test to the point where B students are not underrepresented anymore. And I think this connects to the question from before. So in fact, I think it is hard to believe that such a condition holds, since we believe that several other application features are less informative for disadvantaged groups. And remember, for example, like the example from recommendation letters. But if this holds, then this would happen. On the other hand, when this doesn't hold and the test score doesn't have such a dramatic effect on the total precisions of two groups, then diversity decreases after dropping feature K. So going back to this New York Times piece, like I remember I told you in the beginning, if we believe that the informational disadvantage persists after dropping test scores, and like this is what the article was concerned about, then removing test scores may actually harm those disadvantaged students. And in that case, score is a noisy, but still a helpful source of information for disadvantaged students, exactly as you said. Okay, so clear? I'll take it, so yes. So moving to the individual fairness, similar to diversity, we have that if the removal of the feature K has a similar effect on the individual fairness gap, then dropping test, and if specifically dropping test scores sufficiently reduces or even reverses the information disadvantage of students in the group B, then the individual fairness gap will decrease. Otherwise, it will increase. Same effect, exactly. But what I want to highlight here is that although the effect of the individual fairness gap is ambiguous, this informational loss that the school pays after dropping the test score would actually negatively affect the most skilled students in any group. So we see that if we look at the students above this threshold here, then their admission probability for any group decreases after dropping the test. And this is indeed very intuitive, right? Because if we consider that the school loses a source of information that up to some extent, although it was noisy, but up to some extent helped the school identify high-skilled students, then the school cannot target those people equally well without test scores. And for the same reason of informational loss that I just said, the academic merit will decrease for both groups. Okay, so up to this point, we have compared policies with and without test when the school optimizes only for academic merit. So one might naturally ask whether affirmative action could help. So I don't want to talk like a lot about this. Very briefly, I want to show you the result. So given the estimation process, the same estimation process, so nothing changes, then we consider that at the final selection level, the school may wish to apply affirmative action. And this means that it sets some target fraction tau of students that it wishes to admit from group B. So both in theory and simulations, we studied the effect of affirmative action with and without test, and the results again are mixed. So of course, diversity improves, like this is in an artificial way because we impose a constraint on the actual fraction of disadvantaged students that need to be admitted. But in terms of individual fairness, the individual fairness gap improves for all skill levels, so that's a good thing. But on the other hand, academic merit will increase for A and will decrease for B. So the gap between the two groups will become worse compared to the same policy without affirmative action. Okay, so I see.
Yeah, we have a question.
Yeah.
Yeah, sorry, I just had a quick question about the test feature.
Mhm.
Is it one score or is it like the LSAT where the school can see all the times that you took it? Like, because that gives you also some signal, right? In terms of like maybe more privileged kids have taken it since sophomore year or such.
Yeah, that's a great question. So in this paper, we assume that the school just like sees one score, like this is a test, and we don't take into account what happens when they actually take, like students may take the score multiple times, which of course like is a form of disparity, right? But I want to mention, and I will talk about it later in the latest literature, that there is a recent paper by Karan et al. That actually looks at this question. So what happens when we take the test multiple times? But I will talk about it later. Thanks. Okay, so now I want to come like to the second factor I promised at the beginning of the talk. And like this is another, like the second most important point in this talk. So I want to talk about access barriers to testing. So what we assume here in the paper is that on top of this informational disadvantage that B students have, we also consider that the same group of students might face some barriers to testing, meaning that only a fraction of each group G, so like this fraction gamma G, has access to testing. And all of our results so far consider a setting with no barriers at all, right? But we can now look at whether the previous results change when group A students have greater access to testing than group B students. And this assumption is motivated again by the empirical evidence that I showed you earlier. We know that some students do not take the test due to cost or some other access barriers. And what is important here is that if they don't have a test score, so if they cannot take the test, then they are not eligible to apply to a school that requires the test, even if they were qualified otherwise. Okay. So as a result, dropping the test score requirement expands the pool, and as a result can improve both diversity level and academic merit of the admitted class compared to our previous benchmarks without barriers. And the complete statement of our results is in the paper, but I would just want to show you the main takeaways from that result. And so like I want to pause here because like this is like one of like the second main insight we get. So using affirmative action with target diversity level tau, then dropping test scores increases the academic merit of group G, if and only if this group G faces sufficient barriers. So if this fraction gamma that I told you before is at most like this value here. So like this is a threshold gamma hat G that we characterize in the paper. And a similar result holds for a policy without affirmative action. However, the condition here is more complicated and it depends on both parameters, gamma A and gamma B. And what we see here compared to this case with affirmative action is that diversity may decrease under certain conditions. So I think this result is important because it helps us understand a bit better the trade-off between informativeness and barriers that many people think about. So a big concern of proponents of test scores, if you remember, is that dropping the test would lead to less academically prepared students. And as we saw a few slides earlier, indeed, this is true if all students had full equal access to the testing. But what the results on this slide tell us is that when there are sufficiently high barriers to testing, this is no longer true. And by removing those barriers and letting more applicants apply, we can actually improve the academic merit of the admitted class. So a question here is, will we benefit both groups? And as those statements show, the answer is maybe. It's not clear whether both groups are benefited. We know when they're benefited based on those conditions. So the answer depends on the actual magnitude of barriers that each group faces, and of course the test scores informativeness. Okay, questions here on this or the other results?
I have a question. Did you thought about like having an option of taking the test, that like it's not mandatory to take it, but you can take it and then it's going to be considered?
Yeah, so this is one of the ongoing parts that we have. So like I don't have an answer yet. Like I have like, we don't have, I actually have an intuition of what happens, but we don't have like a formal result yet. So I think like dropping test scores, making scores optional will actually create some type of statistical discrimination again, because if you don't submit the test, then the school might think, okay, you took the test. If you seem that you had the results to take it, then now you're just not revealing the bad score you took. So I think like some like similar effect will arise again. But yeah, that's a great point. Okay, finally, we move to the last part of the talk, which is an application using data from the Texas Higher Education Opportunity Project, and specifically from UT Austin in the period from 1992 to 1997. And we have several available features. Very briefly, high school class rank, standardized tests, demographic features, high school features, and that's important because we will use it, is the economic privilege. So like how the area of the school looks like in terms of socioeconomic status and the resource that the school has. Then admissions and enrollment decisions, we also observe that. And finally, for enrolled students only, the transcript data, so GPA, college, major, number of credits, so on. And the problem we have here is that we can actually not observe the outcome of students who were not admitted or did not enroll. So what we do here instead is that we consider our applicant population as those who in reality enrolled to the university, so that we can observe the transcript data, which wouldn't otherwise have. So instead of admissions, we simulate a setting where applicants need to be selecting for an honors program, fellowship, or college transfer. And for each individual, we use their final GPA as their true skill. And we use class rank, college, and test scores as additional features. And we will use the high school's economic privilege that I told you before to define privileged and disadvantaged groups of students. And then our experiment is very simple. So based on those data, we trained 2 models using OLS and by sampling the unequal number of applicants from each group. And for our simulations, we assume that 2/3 of disadvantaged students do not have access to the test. This is an assumption we made. We also checked other values as well. And at the high level, our experiments show that the answer to whether dropping the test improves our 2 objectives depends actually a lot on the informational environment we're in. So in our first simulation, we considered a low informativeness environment that includes the features I told you, class rank, college, and potentially test scores. And we find that dropping test scores might decrease diversity significantly because high school rank is very, very uninformative for the disadvantaged group compared to test scores. But we do a second simulation as well for a high informativeness environment. So in our second simulation, we use an additional feature, which is the first semester GPA. So we see that using an additional feature that is, of course, very informative for both groups, actually has the opposite effect. So when we drop test scores, diversity increases and academic merit, as measured by the final GPA of the students, slightly improves, right? And I want to say that in both cases, group B students, so we had the capacity of 20%, so we admitted like 20% of the students. And group B students in our population actually composed 40% of that top 20%. But of course, we don't see 40% here. We see even like without tests that much fewer are actually accepted in our simulations. So this is a brief overview. More details about their setup and assumptions can be found in the paper, of course. So moving towards the conclusion, I just want to briefly mention that our paper contributes to a long line of literature in economics and fair machine learning. We connect to all these works either through the modeling assumptions we make or the use of affirmative action and fairness notions. And our model is actually an extension of Phelps' seminal framework to multiple features with non-identical distributions and a continuum of candidates. I don't know if I will have time to talk about these papers, but this paper here and here are also related. And I talked about this paper before, which is about multiple testing. So although this talk focused a lot on college admissions are an example, I really want to emphasize that this is a very simple and general framework that could be used to model several decision-making problems, algorithmic or not. And not only in the context of college admissions, but also applications for education, hiring, and so on. And of course, it is very stylized. I would be happy to discuss these assumptions here. But what I mostly want to say here is that we need more data to understand the barriers students face and the effect of different features and policies in admission. And we don't only need to collect more data, but I think what's more important is that we need to be given access to the existing data as researchers, which is very, very hard if we really want to solve this problem. And to conclude, I would like to reiterate the main message of our paper. Our Bayesian framework studies the effect of testing requirement on academic merit and diversity in college admissions. We saw that the implication depends on 2 things, right, that are competing to each other: the presence of testing barriers and how it affects the applicant pool, and whether test scores improve applicant skill estimates. And again, what we specifically found in our talk today is that test scores and other features variance matters. So it's an important factor and has an ambiguous impact on disparities. Dropping test scores may sometimes lead to a less diverse and less academically qualified class. But if we believe and we find that there are substantial barriers to testing, then dropping test scores can improve both academic merit and diversity. And more broadly, I also want to reiterate that we believe that this multi-feature take on the classic statistical discrimination model naturally fits the study of several decision-making questions and fair machine learning questions, and specifically the design of input features to machine learning tasks. And we hope that it could serve as a useful conceptual framework to explore these problems. So thank you for your attention, and I would be happy to answer any questions in the remaining time.
Thanks a lot for the great talk. So yeah, if anyone has any question right now, please go ahead. We have, sorry, we have 3 minutes left. So yeah, so I see that, well, there are quite a few questions. Or is it just applause? It's applause, okay.
I don't see the chat right now, so sorry, I didn't see the question.
And yeah, there was actually, that was my bad. There was no question. It was just like the emoji when people upload on Zoom. I mean, I guess we don't have any questions, then we can call it a day. So then thanks again, Faidra, for the great talk. It was very nice to have you.
Thank you for inviting us. If you have any question, please feel free to email me or any of my co-authors. And I just want to say that a new draft will be posted very, very soon, like with all the results I talked today.
Yeah, thanks again.
Thank you.
Well, see you, everyone.